Hello, everyone. This is the first part of my talk in the first Geometric Analysis Festival. First of all, let me thank Rudolf Zeidler for the invitation to speak here and present my work. The topic of my talk is scalar and mean curvature comparison via the Dirac operator. And here I'm reporting on a joint paper with Simone Cecchini from the University of Göttingen. All right, so let me start by giving a sort of introductory overview. What kind of notions of curvature do we have in Riemannian geometry? So classically, the kind of curvature which contains the most information is the sectional curvature, which gives you a number for every tangent two-plane. And in dimension 2, this is well understood, and we all know what this is, and has a very concrete geometric meaning. In higher dimensions, it's still well understood, but it's very complicated because we get a number for every two-plane. And if the dimension is very high, we have a lot of different two-planes in different directions, and so we get a lot of data. And to reduce the amount of information that we have to deal with, what one often does is to take certain kinds of traces or averages. The sort of first kind of thing one does is to pass to the Ricci curvature, which then reduces the information in such a way that essentially you only get one number for every unit vector in the tangent space, which is slightly less. And what you do is if you fix such a unit vector, you essentially average or take the sum of all the curvature information over all the two planes that contain this unit vector. And finally, if you sort of average once more, you take one more trace, you end up with the scalar curvature, which is just a number for every point in the space of the manifold. All right. And now, let me say a little bit about how to interpret this thing. So they are defined, the point of view that I take here is that they are defined using formulas in differential geometry, but they have a maybe more concrete geometric meaning. And let us focus in particular the case of positive curvature. That is, assume to begin with that the sectional curvature is bounded by some positive number, and let's rescale this number to be 1. Then we, like from the two-dimensional intuition, we have a sort of concrete geometric picture of what this might mean. So this might mean, if we think of in terms of classical comparison geometry theorems, this kind of means that triangles or hinges are kind of fat. They look like this. So this is what very, very intuitively one might have in mind if one thinks about sectional curvature. If one passes to Ricci curvature, this still has geometric interpretations or geometric consequences. For instance, you get some sort of volume comparison results. And the thing that I actually want to focus on in this talk are diameter or distance bounds. But as you remember from the title of my talk, I actually want to deal with scalar curvature. And there it's just one number, but which is a priori very simple, but it's not so clear what it means. So, so classically, what you might think of here is some sort of infinitesimal volume comparison. And what do I mean by this? So this is sort of a classical fact that the scalar curvature can be used to describe how the volume of small balls behaves if you take the radius going to 0. The following sense that if you look at the volume of a R ball inside your manifold, and you compare this to the volume in Rn with respect to the flat metric, then you can write this expression, essentially the Taylor expansion of this at 0 in terms of the scalar curvature. So this looks like this. So you have a constant term 1 and a order 2 term that depends on the scalar curvature. And then it goes on in order 4. So this is, you might say, okay, this is a very concrete geometric interpretation of the scalar curvature. But the problem with this is that it's rarely used for anything other than stating this fact. And the reason for this is that it doesn't give anything global. So it doesn't integrate to anything on medium or larger scales. It's really just something infinitesimal. So it's for this reason not considered to be that useful. And really what I will ask in this talk is, can we do something else, something more concrete? And it should kind of be in parallel to these diameter bounds that one gets in Ricci curvature. So let's focus a little bit on what this is. So what I'm referring to here is the classical theorem of Myers, which tells you that if the Ricci curvature is bounded below by n-1, where n is the dimension, and as you see here, this kind of corresponds to the normalization of the sexual curvature to be 1. So this is kind of a canonical bound that you might consider for the Ricci curvature. Then the diameter is bounded by pi. And pi is incidentally, or maybe not so incidentally, the diameter of the standard round unit sphere in any dimension. So what this really tells you is that if the Ricci curvature is bounded below by the Ricci curvature of the sphere and your manifold is complete, this is also important, then the diameter of your manifold is bounded below by the diameter of the corresponding sphere. And in fact, something more is true. If you have equality here, then there is a rigidity theorem. This is the rigidity theorem of Chang, the Chang's diameter rigidity theorem, which tells you that if you have the extremal case of Myers theorem, then your manifold must actually already be isometric to the standard sphere. All right. So this is Ricci curvature. Now, as I announced, I want to explain something similar for scalar curvature. So let us ask, what about scalar curvature? And of course, the corresponding bound of scalar curvature that we want to consider now would be n times n-1. This is precisely the scalar curvature of the standard unit sphere. And the first thing that you notice is that, well, something like Myers theorem clearly cannot work. So this is too naive. And the reason is that if you go, let's say, in dimension at least 3, and you look at the n-1 sphere across the real line, then you take this and you just basically take the round metric on the sphere and the standard line element on the line, and you take the Riemannian product metric. Then this will have a constant scalar curvature, which is positive, just because the scalar curvature behaves additively with respect to direct Riemannian products. So the scalar curvature of such a product manifold is really just the sum of the scalar curvatures. And for that reason, you can construct easily a manifold which has scalar curvature equal to n times n-1, which is complete, but which is unbounded. So you don't have a diameter bound like this. And if you don't want something non-compact, but rather something compact, you can, of course, also take a very large circle and take a product with a sphere, and you get a manifold of an arbitrarily large but finite diameter. So you, in either case, you cannot hope for diameter bounds just from the scalar curvature. This is just not what you can hope for. But now, if you look at this example a little bit more closely, then you might think, okay, well, this clearly doesn't work because the scalar curvature in this example is just completely supported on the sphere part here. And maybe we made our lives a little bit too easy this way. And maybe let's consider the same example, but replace the sphere by something else, which does not admit the metric of positive scalar curvature. And maybe the sort of first favorite example that you might, or maybe my favorite example that I would consider here would be to take the torus. And the torus is known by classical results of both Shane and Yao and Gromov and Lawson not to admit the metric of positive scalar curvature. But now you might ask, well, if you take an additional R-line direction here, maybe you can do something. Maybe you can find a complete metric of positive or uniformly positive scalar curvature on such a manifold. And here the answer is also no, this is not possible. And this is also was already answered in the 1980s by Gromov and Lawson, who told us that actually this manifold doesn't even admit a complete metric of positive scalar curvature, let alone one with a uniform lower bound. So this is not just not possible. But let's forget about this for a second. Let's try anyway. Let's see if we start with this manifold and we would like to attempt to construct a uniformly or just a positive scalar curvature metric on them. And maybe the first thing to take would be a product. But okay, a product just doesn't work. But maybe the slightly less naive thing to do would be a warped product. So let's look at a warped product metric on the torus cross the real line or cross an interval. And we sort of use a warping function here. And we keep the flat metric on the torus. And then, well, we can open some books on differential geometry and look up the formula for the scalar curvature of such a warped product. And we see that we get such a differential expression which involves the logarithmic derivative of this warping function that we started with. And then, well, we can just take this expression and try to solve an ODE where we set this to be equal to n times n minus 1 and try to solve it and see what happens. And of course, an ODE can be solved. And in this case, we can actually do it rather explicitly. So we can achieve this equality here for some time. And we get a sort of explicit solution, which looks like this. So if we plug in this, one can check that this expression here will be constant equal to n times n minus 1. And as one sees here, well, this will only remain positive in the interval from minus pi over n to pi over n. And moreover, this function here, which is the logarithmic derivative of this warping function, this also has an even nicer explicit description. This is just a tangent function here. And geometrically, this has an important meaning. This is, if you use this warped product metric, then this logarithmic derivative is the mean curvature of this hypersurface Tn cross x. Or in general, if you have a warped product like this of an interval, then this hypersurface cross-section times x will have h of x as a logarithmic derivative of phi as the mean curvature. And now maybe let's analyze this solution a little bit. For in case n equals to 2, here then you just get the cosine function, and this gives you just a warped product description of the standard sphere. Let's say minus two antipolar points. So in n equals 2, this is well known. This is just a standard sphere. But in higher dimensions, this is something different. So here you get a sort of kind of root description and a kind of root formula of a higher root here. And this in particular means that this metric here is singular at the boundary. Well, I mean, it's of course clearly singular because it goes to 0, but in the sort of two-dimensional case, this actually closes up to be both topologically and metrically to be a manifold. But in higher dimensions, it does not. So in higher dimensions, this, of course, not even topologically is a manifold if you close it up because you have the torus here, but not even metrically, right? Even if it wasn't the torus, even then, this kind of metric, it has a genuine singularity here. And maybe let's plot a little bit how this function looks like. So we see that, you know, as the dimension grows, this warping function sort of crashes into 0 very rapidly. So yeah, that's how it looks like. And these kind of metrics, they will play an important role in what I'm about to tell you. And in fact, what sort of the initial the idea that initiated this work, our work, is a conjecture of Gromov, which essentially says that if you take a warp product like this, then this is actually the best that you can do in certain situations. So even if you think, okay, maybe a warp product is too naive and like do some other kind of metrics, well, Gromov's conjecture says that you cannot do better. So more precisely, the conjecture is as follows. We start with a closed manifold of some dimension, which for sort of some reasons should not be equal to 4, and which has the property that it does not admit a metric of positive scalar curvature, like the torus or like the K3 surface, something like that. And then you consider Riemannian metrics on M cross the interval, yeah, of a positive scalar curvature. And if one analyzes this warp product that I discussed in the previous slides, one can easily see that no matter what the manifold M is, one can always construct such positive scalar curvature metrics. So there's no obstructions to that, to have that on this cylinder. But there turns out to be an obstruction to make this cylinder to be too long. And the conjecture, in fact, says that if you consider the distance between the two boundary components, so let's say we have M, this is our M, and then we look at M cross the interval of some metric. So maybe let's draw a little bit like this. Then this has sort of two boundary components. Let's say one which is denoted by del minus, and another one which is denoted by del plus. And the statement just is that the distance between those two boundary components measured with respect to this metric that has a positive lower scalar curvature bound, this is bounded by some explicit constant, which is 2 pi over n. And it is precisely the constant that you get if you do this warp product example that I began with. And maybe just some history. So this conjecture was originally formulated and also proved in several examples by Misha Gromov in his 2018 article, Metric Inequalities of Scalar Curvature. And there it was proved for the torus and for other related manifolds, which can be whose sort of non-existence of scalar curvature metrics can be proved using Shane and Yao's minimal hypersurface method. Then there is another method that one can use to show that manifolds do not admit positive scalar curvature, and that is the Dirac method, that, or more precisely, the index theory of the Spinor-Dirac operator. And this was proved, several examples where index obstructions are present. This conjecture was proved both by Simone Cecchini and myself, and a more refined version of that now in a joint preprint that I'm going to present in this series of in this talk here. And also, in fact, in low dimensions, in dimensions up to 7, it turns out this conjecture has been proved more or less unconditionally, following the so-called mu-bubble method suggested by Gromov, and this was then worked out in more detail by Daniel Rede, also in a very recent preprint. And at this point, I will take a break, and in the next part of my talk, I will explain in more detail what this Dirac operator method means very briefly, and how to approach this conjecture using this method.